So welcome to our CTSA statistical seminar for November. Today I'm going to look at modeling, in particular here, atrial fibrillation with observational data. And I want to look at a number of things that need to be considered when you have observational data and you want to look at just even relationships, but more in particular if you want to model some particular outcome. So the data that I'm going to use is from the Hypertrophy Cardiomyopathy Registry, or HCMR. And the issues that I want to talk about include missing data and multiple imputation, then variable selection for the model, and in particular a fairly new way of model development called the elastic net. We have time to event data and competing risk as well. In other words, risks that may negate the actual outcome. And then since we're looking at time to event analysis, one of the issues related to that is what we call non-proportional hazards. And so we're going to take a look at how we deal with that. And then because we have multiple events, when we need to look at how we handle that rather than just a single event. And then we want to talk about at the last here, model discrimination and calibration and model validation. I want to, before we actually get into this, I want to just say that if you have questions, use the Q&A mode, and then at the end I'm going to leave a few minutes and take a look at those, and I'll answer as many of those as we can. Also, the presentation here is being recorded, so it'll be made available to those who have registered. I believe it's on YouTube, but Georgetown will send out the link to that to those who are registered, and then also we will send out a set of the slides to those who are registered. Okay, so the HCM, Hypertrophic Cardiomyopathy Registry, is a study that was sponsored by the NHLBI. And the PIs, Dr. Kramer and Dr. Neubauer from the University of Virginia, and in the EU from the University of Oxford. Dr. Weintraub is head of the Data Coordinating Center, which is here at MedStar Health Research Institute. And I wanted to acknowledge Sarah Fay and Julissa for their really hard work in putting the data together. So the HCM study were patients who had a diagnosis of HCM between the ages of 17 and 67. Our enrollment began in 2014, extended through 2017, and we enrolled a total of 2755 patients. And these were from 44 different sites in 6 countries: the US, Canada, the UK, Germany, Netherlands, and Italy. Follow-up is ongoing. At the time that we did this study, the average follow-up was nearly 4 years. And the primary outcome that we were interested in is sudden cardiac death. Fortunately, I guess you could say that this is somewhat of a rare event, so we need more follow-up time to have really enough events, sudden cardiac death events, to do a proper analysis. And so we're looking for the time when we have at least 100 sudden cardiac deaths. But the secondary outcome that we're going to take a look that we did now is atrial fibrillation. So our study was recently published, at least it's in press. I'm not sure if it's actually in print yet, in the Journal of American Cardiology, Clinical Electrophysiology. And so I've listed the authors here, and then also the institutions of the authors. So you can see that it's quite a broad representative of academic institutions and research centers that are involved in this study. Okay, so the first issue that we want to look at is the missing data issue. And so in any study, you're bound to have missing data when you do human research. And I know that every effort is made to not have missing data, but it just, for one reason or another, occurs in research. And the issue is that the missing data, or the extent of the missing data, might influence the outcome of or the results of the study. In other words, the loss of individuals may result in a different outcome or different conclusion than if you had all of the data available. Now, a sort of a rule of thumb is if you have 1%, or some people maybe use 5%, or less of your sample have missing data, then you can just drop them from the analysis and do the rest of the cases, because that few missing isn't probably going to make that much difference. But if we do have more extensive missing values, then what we can do is we can impute the missing values and produce complete data sets to analyze. And one issue here that at least I have with doing multiple imputation, if you have a lot of missing data, say nearly half of your patients or half of the sample are missing data, then imputation, at least in my mind, is questionable, although you can still do it, but that's a lot of missing data to impute. So I want to discuss just a little bit here of the missing data mechanisms, because these are important in terms of how we impute missing data. And so if we have data that's called completely or missing completely at random, that means that the missingness mechanism is not related to the outcome or to any covariates, predictor variables that you have in your data. And so that's that's the strongest of assumptions, that it's not related to any of the variables that you have. Missing at random means that missingness is not related to the outcome, but it is maybe related, and probably is related to the covariates. And so most studies are going to make the assumption that data is missing at random, because then we can do multiple imputation methods that are fairly easy to do. If we have data that's not missing at random, then that means that the missingness mechanism is related to the outcome and probably to covariates. And we talk about missingness being ignorable or non-ignorable. But if it's related to covariates, and especially if it's related to the outcome, then it's non-ignorable. And so, is the missing at random a reasonable assumption? Well, the thing is that you never know for sure why data is missing. But there are instances where it's likely not missing at random. And one of these situations is when you have an outcome that's assessed over a fairly long period of time. And as an example, the Courage trial that I was involved in some years ago, we assessed quality of life at baseline, at 1 month, 3 months, 6 months, 12 months, and then yearly thereafter from enrollment. And some patients were followed out to 6 years or 72 months, after enrollment. But as you would guess, and what was noted, that with each assessment period or time when quality of life was assessed, you had fewer and fewer patients. And so is this data that's missing at random? Well, probably not, because over time, what you would expect is that people who are responding to your questionnaire, months and even years after the study began are likely the healthiest patients. And so dropout is probably related to how healthy the patients are. So another kind of really simple example is if you had a study where you were looking at weight loss. And so one of the requirements was for you to come in every month and get weighed to see how you were doing on your weight loss program. So if you say left for your appointment to get weighed and you backed out of the driveway and some of the car kind of ran into you and you had a fender bender, and so because of that you missed your appointment to get weighed. So that particular data in that case would be missing at random. On the other hand, if you before you leave for your appointment think, I think I've gained weight and so I don't want to go in and get weighed. In that case, your data is missing, but it's missing not at random because the outcome would have been related to the missing mechanism. So it's assumption that we have to make, and whether the data is missing at random, and is that a reasonable assumption? So we never know for sure, but we need to sort of think about what the likelihood is that our data is missing at random. So in our study here, we did assume that the data was missing at random. I'll make some comments about that later on. But so what do you do when you have missing data and you want to then impute the missing data? So what you do is you generate M complete data sets, and usually the rule of thumb is you do 3 to 5 complete data sets. And then you analyze each set individually. In other words, whatever the particular statistic you're doing, you do that for each set. Then you combine the result for each data set. And so, for example, if we're doing like regression, and so we get a regression coefficient of beta. So if we did, say, for example, 5 different data sets, we would take the regression parameters, sum them up, and divide by however many analyses we did. So that's the sum of in this case, the beta is divided by 5 if we did 5 data sets. Calculating the error variance, though, is a little more complicated because we need to take into account both variance within each data set and then variance between the imputed data sets. So there's different ways of doing imputation. One that you see more often than you might like is what's called simple imputation, where you substitute a mean value or a mode if you have categorical data. Generally, that's a bad idea. There's maybe some cases where that might be appropriate, but by and large, it's not. And the reason is that, of course, if you're substituting in a constant across all missing data, and so that's not really appropriate. Linear regression is just you regress on the using your available data on the outcome. And then for the missing data, you draw a value from a theoretical distribution, like the normal distribution. The problem with doing that, if you draw from a theoretical distribution, that you might get values outside of your observed values. The one that we used, the method that we used in this study, and which is sort of one that I particularly like for continuous variables, is what's called predictive mean matching. And so this is based on a regression. You regress all of your covariates on the outcome, and then you get a value from the predicted, from a value that's predicted by the regression from the observed cases, and then you have a set of patients that or subjects that have a similar predicted value, and then you assign the value to the missing value, not the predicted value, but you randomly select one of the observed cases that has the data that not missing, and then whatever that value is for that case, you assign that to the missing case. So in doing this particular method, you always will get a value within the range of observed values. If you have dichotomous or categorical data, then we'll do some sort of logistic regression and calculate a probability from the observed data. And then we'll take random draws from the binomial distribution that fit the observed data. So in our study, we have both continuous and categorical data. So we're going to use predictive mean matching and then some form of a logistic regression to impute values. So I'll give you an example here of our data. So I've kind of grouped these into different categories. So we have demographic, clinical variables, a couple of biomarkers, BNP and troponin, and then genetic data at the bottom there. And so out of the 2755 that we have, on the far right column, you can see the percent of missing. And so for the demographic values and most of the clinical values, the amount of missing data is very small, right around 1% or less. For the biomarker and genetic variables, you can see that missing is a little higher, from around 4 or 5% of data is missing from those variables, which is what you'd expect, since they're not as easy to acquire as the demographic variables. And then a couple of other categories here. This is CMR, the magnetic resonating variables, where we get left ventricular mass, EF, and the right ventricular mass, and so on. And then with morphology, which is also data that you would get from a picture, basically. And so you can see here that the percent of missing for like the CMR data is all the same. Well, why is that? Well, that's because all of these variables are obtained from one image. And so if you don't get the image, then you don't get any of the data. So that's why the missing is the for each of these variables, the percent of missing is the same across all of them, because if a patient doesn't get the image, then they're missing all of those variables. So the most that we're missing is in our CMR data, where we have a little over 6% missing values. So the way that I did this, if I can explain this, is that that when I did the imputation, I used variables that I had complete data for, either to begin with or that I imputed myself by hand. And then I used those values to impute the next variable in a sequential fashion from least missing to most missing. And so I did this 5 different times to come up with 5 complete data sets. And then I did another additional 5 data sets where complete data were generated with the order of imputation for variables just chosen at random. So in case that the way that I did it the first time, going from least missing to most missing, resulted in some sort of oddity in the data, that the order in which they were imputed was randomly assigned. So I have 10 complete data sets now for analysis. Just as it turned out, there wasn't any real difference as far as the distribution of variables that were imputed, regardless of which way I did it. So having 10 data sets, then what that means is every analysis I do, I'll be doing it 10 times. And so for my regression coefficients, as I've mentioned before, that's just the sum for every regression coefficient. That would just be the sum of the coefficients divided by 10. And so that would give me an estimate, an overall estimate of what the regression coefficients were. The standard errors, as I mentioned, were a little bit more difficult or complicated. So I have 2 components here that I need to compute, where W bar is the average variance of the 10 data sets, and then B is the average sum of squares. So that's the average minus each individual variance squared and then divided by 10. And so to get my standard error for the regression coefficient, I have the formula, the square root of W bar plus the number of imputations plus 1 divided by the number of imputations times the quantity B. And so that's the standard error for each regression coefficient. So in the analysis sample, there were 77 of the 2755, there were 77 that had permanent atrial fibrillation. And so those individuals were excluded from the analysis. There were an additional 47 that either had no follow-up value or a few of them, I don't remember how many, were missing actually all of the 46 variables that we wanted to use to predict atrial fibrillation. So that left us with 2631 patients for the analysis. And of these, 96 patients had a total of 127 atrial fibrillation events. And in that 2631, there were 24 deaths from any cause that we'll have to take into account. So when we come then to variable selection, so we have our outcome, atrial fibrillation, which is yes or no, but then we're looking at the time variable as well from enrollment to events. So we're going to do Cox proportional hazards regression. And as I mentioned, we have 46 potential predictors of atrial fibrillation. So how are we going to select those variables? Well, a typical way that's been done in the past, and actually still is to do stepwise regression. And you can do that for the Cox model as well, either backward or forward. But when you do regular regression, you have to have more subjects than you do variables. And a kind of rule of thumb is that you need 10 to 20 subjects for every variable that you have in your regression equation. And then also, ordinary regression relies on statistical significance for variable selection. So if you do stepwise, you have to set a significance level for entry in, and then you also have to set a significance level for removing variables from the model. There's a fair amount of literature on why this is not a real great way to do model building. And another not so great way that I just might mention in passing here is that you do a univariate analysis on all your potential predictors, and then you choose the ones that are statistically significant and put those in your multivariable model. Well, well, all I can say about that is don't do that. That's a really bad way to form a model. So the method we're going to use is what's called elastic net or penalized regression. So rather than select variables based on statistical significance, we're going to select variables by penalizing the regression coefficients. And in elastic net, the two sort of extremes here of penalizing is ridge regression and then what's called the lasso, or at least absolute shrinkage and selection operator. And basically what this method does is it reshrinks regression coefficients towards 0. Now, if you use just the lasso, that's a popular method because it shrinks the unimportant regression coefficients to 0, to actually 0, whereas ridge regression doesn't. So you've still got to make a decision about the variables that you want to include in your model. So the really neat thing, or a neat thing with penalized regression, is that you can have more predictor variables than you have subjects. So if you have sparse data, then this is what you would need to use. So that's the as far as variable selection goes. This is like I say, it's a more modern method for developing models, and one that's used fairly extensively now in the literature. So the way that we chose, or that I chose, variables for our model here is among the 46 predictor variables. We applied the penalized regression to each of the 10 imputed data sets. And then for each of these 10 data sets, the variables that were selected were ranked according to their order of selection. And then the way that we chose variables to be in the model was variables that appeared in all 10 of the data sets. And so here is the variable identification for each of the 10 data sets, and they're rank ordered in the order that they were chosen. And I listed 13 here, variables that were selected by the penalized regression. And so you can see that for every single data set, all 10 of them, the first 2 were selected in every single one, the index LA volume and contractile percent. And then you can see that there's some difference after that among the 10, but there are variables in here that do appear in all of the 10 data sets, for example, like BMI and mitral regurgitation. So what I did then is I took the variables that appeared in all 10 data sets, and then so this is the ranking then of the variables that were in all 10. So in our penalized regression, there were a total of 17 variables that were selected out of the 46. And so we chose the 11 that appeared in the penalized regression analyses in all 10 of the data sets. There were a few others that did appear in some of the data sets, but we excluded those primarily to make the analysis a little more manageable. So we have 11 variables that we're going to include in our initial analysis. And so the analysis that we're going to do, of course, is Cox proportional hazards. And we're going to do that for each imputed data set. So one of the issues then that we need to address is competing risk. And so in this case, death would be a competing risk for atrial fibrillation. So what we mean by a competing risk is an event that can occur, an event that's different from the primary event you're interested in, that's going to affect the distribution of the analysis, in this case, the distribution of the hazard ratios in the Cox model. So the method that's typically used in dealing with competing risk is that of fine and gray. However, the fine and gray method only applies to time to the first event. So when we have multiple events, then it's a little bit more complicated. But I believe there's literature now that shows how that can be done. So what we did then is to compare a Cox model to the competing risk models, where we just censored observations at death. Because with the competing risk method, all of the deaths stay in the analysis at each iteration. So the people who died are actually never censored out of the competing risk method. So what we did then is we compared the competing risk with the usual Cox model, where we just censored it, observations at death, and compared the regression coefficients, and then also compared the information criteria, CHUCCTS, and the Bayesian information criteria. So what we found, which was actually kind of nice, is that there was very little difference between the competing risk and the non-competing risk Cox regression. And so just for example, here I have the first data set and the 11 variables, and looked at the competing risk regression coefficient for each one, and then the non-competing risk regression coefficients. And then I just did the difference between the coefficients. And so you can see that they're really pretty similar. And so that the competing risk isn't much different, or the non-competing risk isn't much different. And so what we chose to do then was to just go with the regular Cox regression, where we censored observations at death, because that's much easier to work with in the competing risk model. But because there wasn't much difference between the two, we felt that we were justified in doing that. So so all of the subsequent analyses that we did, as I mentioned, we censored them at their date of death. Okay, so the next issue then, because we're doing Cox regression, proportional hazard regression, we need to consider the issue of whether the hazards are proportional over the time period that you're looking at. And so there's actually a statistical test you can do for that, but an easy way is just to compute or to construct Kaplan-Meier curves of your function of your Cox model function, or just if it's just a simple, say, 2 treatment model where you don't have any covariance. And so if you have proportional hazards, then the survival curves or the event-free curves are going to be what we call parallel. But if the curves are non-proportional, then you're going to see something like we have on the right-hand side here. And so that's an indication that we have non-proportional hazards. So we had, and then in addition to that, then we need to take into account the fact that we have multiple events. So we're going to do an analysis. I did an analysis where we looked at just the occurrence of the first event, and then looked at the multiple event, did a multiple event analysis. So as I mentioned, we had 96 patients with a total of 127 events. And so there were 85 with 1 event, 6 with 2, 2 with 3, and then 1 each with 6, 8, and 1 with 10. So to assess proportional hazard, there's a way of doing that, a test that can be done. But if the proportional hazards assumption was not met, then what you typically do is you stratify your analysis by the variables that are contributing to non-proportionality. What non-proportionality implies is that there's an interaction between some of the covariates that you have in your model. In other words, the hazards are not the same for some particular group of patients, like male, females, or race categories or age categories. So I wanted to just have a concrete example here of what a multiple event data structure looks like. And this is the way you actually would set it up to do the analysis. So we have our first patient here. Well, for each patient, you have a start and stop time. So the first patient here has an atrial fibrillation event at 12 months. And then I have a couple of covariates just here to show you how this is appears in the data set. But our second patient has 2 events, one at 15 months and then another one at 27 months. So their first line of data is they start at 0, everyone starts at 0, at 15 months, and then they have an event. Then the start for the next time period is 15 months, and then they have another event at 27 months. And so I have a variable here I've called order, which in some statistical software packages you need to include this in the algorithm to do the analysis correctly. And so our third patient here has 3 events: the first at 6 months, the second at 18 months, and the third one at 31 months. So that's just sort of that is a concrete example of how the data is organized for when you have multiple events. Otherwise, for single event, the only date you need here, or the time that you need, is the time of the event. So if these were just first events, then we would just need the stop time here, the time of the event. Okay, so then the last thing that we are going to need to look at is model discrimination and calibration as far as model fit goes. And so for model discrimination, the statistic that we're going to look at is called the C index, which is the same thing as the area under a receiver operating characteristic curve. And this is an index that ranges from 0.5 to 1. So 0.5 means that you have no discrimination. That is, you can't, from your model, you can't tell whether a person has the event or not, where an index of 1 means that you have perfect discrimination. Calibration is the agreement between the observed and the predicted outcome. And so what is typically done here is that you get you regress the observed on the predicted either probabilities or the outcome, and you look at the slope. And so if they're in agreement, then you're going to have a slope of 1, which would be perfect calibration. So if you have a decent model, then you want to have a calibration index that's close to 1. So it turns out, if we look at the results here, that for all 10 data sets, the proportional hazard assumption was not met. And it turned out that age was the contributing factor to non-proportionality. And so if I were to put interactions in my model, what this would mean is that there were significant interactions of age with volume, with contractile percent, and with BMI. And so the remaining models that we developed, that Cox models were developed, were all stratified by age. And so, as I mentioned, I had 11 variables that came out of the elastic net. But of course, what I would like to do is I'd like to reduce this even more. And so what I'm going to do is I'm going to start out with modeling atrial fibrillation with the 11 variables. And then I'm going to see if I can take some out and still get a good model that's comparable to the model with all 11 in there. And so typically what you do is you exclude one variable at a time, and then you do the likelihood ratio test, which is -2 times the difference in log likelihoods from the model. And this turns out to be distributed as a chi-square with degrees of freedom of the number of parameters in the full model minus the number of parameters in the reduced model. And so then you can get a statistical test of whether the reduced model is any different or is different from the full model. And if it is, then that means that you can't, whatever variable or variables you took out, you can't predict as well as you can with the full model. So the models, the reduced models that I came up with were BMI, the index volume, contractile percent, mitral regurgitation, and history of arrhythmia. And so now this model is stratified by age. So that means that I can drop history of atrial fibrillation, reservoir percent, diabetes minority, and the New York Heart Association variable from the model. And the multiple event model included the same variables as the first event models, except for history of arrhythmia. And so then the regression coefficients for a single model were estimated by combining the results over the 10 data sets. I did that both for the first and the multiple event models. And as I mentioned before, the standard errors I've calculated taking into account both within and between imputed data set variance. So here's the output. I'll go over this because I think this is fairly informative of how I'm doing this. So this is with my 11 variables in the model. There's 10 here, and then it's stratified by age. So the log likelihood statistic that I get is given up here in the output, and you get this whatever statistical software you get, the log likelihood statistic here. This is a number that applies only to the model you're doing. You can't, if you're going to use this, you have to have the same number of subjects and the same set of variables. You can't use this for anything else. So when I look at the results here from my model with all 10 variables actually, and then stratified by age, I'm going to look for some that I think that I can remove from the model, and then I'll test it and see if I can remove those and still come up with a really good model. So the way that I do this, and when you can use other criteria, so just look at the p-values here for the different variables or their confidence intervals. So these two here have a very large p-values, fairly wide confidence intervals. So I might think that, well, maybe these would be good choices to remove from my model to begin with and see what I get. So I did this, and so I removed these, removing one at a time, which does take a while if you have a lot of variables. But nevertheless, what I came up with then was a model that had 5 variables in it for the first event: BMI, history of arrhythmia, contractile percent, volume, and mitral regurgitation. And so what I want to do now is I want to compare my reduced model here with the model with 11 or with 10 variables in it. So you notice that I have a log likelihood statistic for this model, for the reduced model. And so I compute my statistic, which was 2 times the difference in log likelihoods, which comes out to be 5.9. And you remember that I had 10 variables in my full model, because both of them here are stratified by age. So my degrees of freedom is 10 minus 5, or 5. And so my p-value here, my chi-square is 5.9. And so, of course, with 5 degrees of freedom, that's not anywhere near significant. So I have a non-significant log likelihood statistic here. And so I can conclude that my reduced model is just as good as my full model with 10 variables in it. But even more important than the p-value here is the fact that if you have a perfect model, then the degrees of freedom for your chi-square is going to be equal to the chi-square itself. Now, that, of course, that never happens that you have, that anything is perfect. But you notice here that my degrees of freedom 5 and my chi-square value of 5.9 are really pretty close. So I can conclude from that here that I have really a pretty good model, reduced model. And so as you look at this, you see that some of the p-values for some of these variables are not what we call statistically significant. But that doesn't, what we're interested in here is this log likelihood statistic, not the individual p-values, because remember, what's predicting here is the combination of these variables, not any one variable in particular. So you can have in your final model here, you can have some variables that are not statistically significant, strictly speaking. But the issue is, if you remove this variable from your model, in other words, if I only had BMI, contractile percent, volume, and mitral regurgitation, then it turns out that the model is not as good. In other words, I get a significant p-value here for the log likelihood ratio. So you want to keep that in mind as you develop predictive models, that it's the model that's predicting. And of course, you'll probably get reviewers who say, well, why is there a non-significant predictor in the model? Well, that's the reason that you would have it in there, is because if you take it out, then you don't have as good a model. Okay, so then the next question is, so how are we going to present these results? And so one way of doing this, because we've stratified by age, so one way we might think about doing this is to divide age into groups. And so a typical way to do this is by tertiles or quartiles or quintiles. But a better way of doing that, because those are arbitrary divisions, is to use splines to determine age cutoff values to visualize the impact of non-proportional hazard. And so I'm using restricted cubic splines to come up with cutoff values. And it turns out that the best fitting one was a spline with 3 knots at ages 32, 52, and 62. And it turns out that these ages are cutoffs for the 10th, the 50th, and 90th percentiles of the age distribution. So what I'm going to do is I'm going to use these age groups to plot my Cox models of the atrial fibrillation free functions. So, so here's the table for the time to the first event. So my first column here, I have the overall model. So I have like 26, 31 patients, 96 events. And so these are the hazard ratios, the predicted hazard ratios and their confidence intervals from that's used by averaging over my 10 data sets. So you can see that BMI has a quite an impact on atrial fibrillation. That is, people with a higher BMI have a greater hazard of getting of experiencing an AF event. And I've done this rather than in 5 units, rather than just 1 unit, make it a little more readable. And so volume index indicates that also that there's a significant increase in the in AF events as LA volume increases. For contractile percent, it actually decreases. So for the contractile percent, we say that's protective of an AF event. And then for mitral regurgitation, again, that increases the likelihood of an AF event, as does history of arrhythmia. And then it turns out that I have decent fit statistics here. So my C index for the overall model is 0.75, which is, at least in mine, that's kind of okay. It's not real great, but real great would be 0.8 or better, but 0.75 is pretty good. And then my calibration index is really good. It's 0.94, so you can see that's really close to 1. So then what I did was to take each of the 4 age intervals and look at the hazard rates or the hazard ratios for each age group. And so you can see some interesting differences here and why there's interactions between some of these variables. So for example, like for BMI, the youngest patients have the highest hazard ratio for AF, whereas as you get older, it's not, the hazard ratio is not as great. And then so we go down through each of these other variables and we can see differences. Like for example, with contractile percent, we can see that for those with the oldest patients, that we have even a less or a smaller hazard ratio than we do with the younger. So you can see again why there's interactions between age and some of these variables. There was no interaction between age and mitral regurgitation or history of arrhythmia. So that was for the first event. This is the same thing for the multiple event analysis. And so we have, again, in our overall model, we now have 127 events, but the results are fairly similar. We have a big effect for BMI, LA volume, less, again, for contractile percent, meaning it's protective, and then again for mitral regurgitation. And then these are the hazard ratios by the age categories. And so again, for BMI, you can see that for the youngest patients, BMI is a higher BMI is not a good combination for an AF event, whereas for the older patients, it's not so much. So then we also then did the graphs, the Cox Model Graphs, and again, these show basically this, because they're done by the age groups, the effect of BMI, and here I have a BMI at 25, 30, and 40. And so you can see, for example, like at the oldest patients here, BMI doesn't have, it's much of an, isn't making much of it, it doesn't have much of an effect. And then I won't take time to go through the rest of these, but for example, like for contractile percent, which was protective, then you can see that for the lowest contractile 25% has a huge effect for those who are elderly, or the more elderly, where it has less of an effect for the younger patients. Okay, and then so finally, or not quite finally, but these are my calibration plots where I'm plotting the observed versus the predicted. And again, you can see that we have really pretty good agreement here between the observed graphs and the predicted graphs. So our, as you remember, our calibration slope statistic was around 0.94, 0.95. So really pretty good agreement there. So basically, the only other thing to do, which I actually did, although we didn't report it, is to validate your model. And of course, the ideal here is to apply your model to a different sample of patients. But usually you don't have a different sample. So some ways, other ways this is done is to split your sample, where you use part of it for development and then part of it to do your validation, to test it on. That's what cross-validation is, except that you do it a number of times rather than just once. So like tenfold means you draw 10 different development and validation samples and estimate your regression coefficients from that. And then finally, which is what I did, is to do random draws, to do the bootstrap, which is random draws with replacement. So this is just my bootstrap results here, and putting it in a table. These were the hazard ratios from my overall model, and then from the bootstrap, the bias corrected, you can see that they're really pretty close. The ones that are a little further away are mitral regurgitation and history of arrhythmia, but otherwise they're still pretty close. So I can conclude that my model validation doesn't have very much bias in it, or not too much bias anyway. Okay, so I want to end up by saying that when you do prediction models, you need to account for missing data, have to make some selection of a method for selecting variables for your model. You need to look at the model goodness of fit, and then model accuracy or discrimination calibration, or if you're doing a linear model with a continuous variable, then you'd look at the R squared, and then then you'd want to do model some, use some method here for model validation. ElasticNet software is available in SAS data and R, it might be in others or as well. And then I have some references here regarding the study that we did and some of the methods that we used in the study. And then at the end here, I have a link. I hope it comes out as a link to a nice presentation of penalized regression. If you're interested in looking at that, this is sort of a little more mathematical oriented, a little more technical, but still really pretty good. So I see that I'm really out of time here. I will end there, and then thank you for your participation. If you do have any questions or any things you'd like to share, or any comments you'd like to make, you can contact me at my email address here at MedStar. So again, thank you for your time, and we will not have a seminar in December because of the holidays, and we'll start back again in January, the third Friday in January. So again, thank you for your time.